today I'm going to talk about the carbon stars in the exposure spectral library. So first, what is the exposure spectral library? So XSL, it's a moderate resolution spectral library built thanks to an ISO large program and using the exposure spectrograph. So as you may know, exposure is a 3-arm spectrograph covering the wavelength range between 300 nanometers until 2500 nanometers. And so in one shot, we've got all this wavelength range. And we've got a resolution about 10,000. So in our library, we've got more than 600 unique stars. And it's interesting to note that we've got at the end more than 800 spectra, which means that we've got repeated observation on purpose, of course. And this is interesting and it's quite valuable for the variable stars. If you want to learn more about XSL, you just have to wait this afternoon for the review done by me. So when we built our library, we tried to cover as much as possible the H-layer diagram. So to do so, we got some stars from MILES, from IWSSL, LEAK, IDS, but we put also lots of emphasis on the cool stars. So we got some AGB stars from Lancelot Wood, IRTF specs, and we tried also to do different metallicity. So we got stars from the LMC and SMC and so on. But today, in the presentation, I'm just going to focus on the TP-AGB. So why do we care about the TP-AGB? First, because it contributes up to 40% of the total luminosity of intermediate age population. And furthermore, if you underestimate the contribution of the TP-AGB to the set of galaxies, you can screw your stellar properties like masses and so on. And last but not least, it's on the TP-AGB that a star is going to evolve from an oxygen-rich star, so with molecules like titanium oxide, vanadium oxide, and so on, until a carbon star. So a carbon star is a star with a ratio of carbon over oxygen more than 1, and you've got some typical features like, not MERN, but you got like C2 lines, CN lines, and so on. So on the left, you can see some example of synthetic carbon-rich spectra. So if you look at libraries containing carbon stars with a resolution high enough, so you can mention IRTF with 8 carbon stars, Lancelot Wood with 7. And luckily in XSL, we've got 35 carbon stars from the Milky Way and the Magellanic Clouds, and covering G- scale between 1 and 3. So on the left, you can see some spectra from our sample. So they are ordered by increasing G- scale from top to the bottom. And the first thing that you have to note is that everything that you are seeing is signal. So it might look noisy or ugly or whatever you want to call them, but carbon stars are beautiful and everything that you see is signal. You can also note that when you go from the bluest colors towards the reddest, you've got like a progressive shift of the SCD towards the reddest wavelength, and you end up with a kind of plateau in the cable. Here you can find more examples of our carbon stars. So just some zooming over some features. So for example, the CN around 1.1 micron, the C2 around 1.77 micron, and the other feature like the CO in the cable. What is interesting in our sample, besides the fact that we got lots of carbon stars, is that we got a bimodal family. So if you look at the figure from the top, which is just a zoom of a figure that you showed previously, so the two orange spectra, they've got roughly the same colors. But if you look at the bottom one, you can see that you've got an absorption feature at 1.53 micron, which is usually associated to HCN and C2H2. And just based on visual inspection, you would like to say that the bottom spectra has a smoother appearance compared to the upper one. On the figure on the corner, you can also see the difference between a spectra with the feature and without. And this feature is thought to be an overtone of a feature at 3 micron, but of course the exposure spectrum stuff 2.4 microns, so we can see it. So to quantify all that you can see by just visual appearance, we define some spectroscopic indices. So the first indices that we define is the one on the left. So we try to measure the strength of this feature at 1.53 micron. We separate our carbon stars into a bin of colors, and we also separate the stars with and without this feature at 1.53 micron, just based on visual inspection. So what you can see on the left, the black points are just the median of each bin. And you can see that for the star with the 1.54 micron feature, so in a way, and without, you get a clear separation, at least for the star with this absorption feature. We also try to quantify this smooth appearance that we can see in our spectra. And to do so, we define the two indices that we call RMS, H, and K. So a measure of the high frequency in the H band and the K band. And you can see that when you increase the color increase, so you go towards redder stars, so the high frequency augments, in the H and K band. But if you look at the stars with the 1.53 micron, they stand in a corner, and so they feel like they really have a smooth appearance. And so what we think is that these stars are in a kind of cocoon of circumstantial dust that's created. So to clarify this picture and also to determine the stellar parameters of our stars, we compare them with models. So we use some models developed by Haringer et al. 2016 in the framework of their work done in 2009. And so they are carbon wedge model of atmosphere, very high resolution, so 200,000. And it's important to note that these models are hydrostatic and dust-free, which means that we know that these models will be good to reproduce warmer carbon stars without pulsation. But when we go towards redder carbon stars, and because our G-scale go up to 3, we know that these models might not be good, but it's a first step. We just want to see what we can do with hydrostatic models before going into more complex models. So if you look on the left, you can see a high-resolution model in black, and the red one is just a smoother version of the model. So just want to see that by smoothing the high-resolution model, we are going to lose the information about the continuum. So to do our comparison between our observation and the models, we did a chi-square minimization with a multiplicative polynomial, and we did the analysis over two wavelength range. So what we call the visible, so between 0.4 and 1 micron, and what we call the near-infrared, so between 1 and 2.4 micron. And the idea was to find if the parameters defined from one wavelength range agree with the other one, which is of course not always the case. On the right, you can see the grid of parameters. So each square represents a temperature. So we've got a grid of well, we got different temperatures, surface gravity. We got two values of metallicity and different values of ratio of carbon over oxygen. So here it's a color plot showing our observation as black, like field symbols, and the open symbols are for the models. And the green points are for the Lyra tip star. So you can see that when you go towards reddish color, you got like a clear separation between the mirrors type stars and the non-mirror type stars, but the separation is not so clear at bluer colors. Furthermore, you can look at the orange line, which it's just the extension. So we redone one of our model by using the Cardelli law, just to see what we can expect when we are going to redone our models. And you can see that clearly all these models, all this observation, we won't be able to reproduce the same just by using a simple extension law. But so we know that things are going to be complicated and we won't be able to do it, but we just want to see how things are going with allostatic models before going to the dynamical models. And I'm going to explain everything about the different group later. So a spoiler for the temperature. So here I'm showing the temperature obtained over the visible wavelength range and the infrared as a y-axis. And just for the three groups, the first three groups, and D. And you can see that the temperature fonts are, I would say, within the hours or each other, but we tend to have a warmer temperature in the visible. And by doing the comparison, usually we find that typical surface gravity form for our sample, it's log G equals 0, and metallicity of minus 0.5, which is, I would say, typical for our sample of stars. So let's move now to the first group. No, that way. So the stars from group A are stars with a G minus K minus 1.2. So all the stars here. So you can see that two of the stars are in gray, just so they lie outside of the range of parameters because the highest temperature in our model is 4,000. So we already know that we are not able to reproduce them with the grid of models. And just by looking at the literature, so it corresponds to the two spectra there. We found the temperature in the literature 4,500 Kelvin, more than that. So we are not going to consider them in our sample. As I've got 35 carbon stars, I'm not going to show plots for everything, just a sample of carbon stars. So if you want to see your favorite object later, just come to me. So here is an example of some fits for the stars from group A. So on the left is for the visible, on the right for the near-infrared, and the upper plot shows in the black our observation. In red, it's a model. The orange line is the weights that we apply. So for example, in the near-infrared, we put a weight of 0 in the deepest region because we know that we can't reproduce them. The green line below is residuals, and the blue line is the best model minus an evaluated version of the best model. And so what you can see, for example, for that case, is like if you compare the residuals with this, what we call this unsharp mask, we can see that the residuals are smaller compared to this mask, saying that our model reproduces well our observation. And so in that case, you can find that the parameters agree between the two wavelength range, visible and infrared. And for most of the stars from the group A, we find a temperature above 3,600 and a good agreement between the visible and the infrared. But on the corner, so you can see all the chi-square values that we got. And the red one is the best value, and the magenta poles are all the values that we consider acceptable. So you can see like the mirror bars. So let's move now to group B. So group B is just a stars between with a G minus K between 1.2 and 1.6. So if you look at the color plot, you can see that there is a good overlap with the grade of models and observation. So we expect to be able to reproduce these stars, I would say, very easily. And so you can get an overview of our carbon stars on the right. So let's look at the parameters. So as usual, visible on the left and infrared on the right. And what I want to point here is like in the near-infrared, we find a temperature of 3,400. But if you look at the visible, it's like 3,500. Okay, you can say, okay, fine. 100 of Kelvin of difference is still good. Well, at least I consider it good. But it's interesting to note that this higher temperature in the visible, it's compensated also by a higher value of carbon over oxygen. Because in the near-infrared, you got 1.4, and in the visible, we got 2. So we already see the degeneracy between the parameters, at least the degeneracy between the temperature and the ratio of carbon over oxygen. And the parameters found for all the stars are roughly between, at least the temperature between 3,200 and 3,800, and there is a good agreement between the temperature found in the two wavelength range. So if we look now for the stars from group C, So we are getting closer to the limit of what can be done with hydrostatic models. And we are getting more and more affected by the circumstellar dust. So we know that we will be able to derive the parameters, but we might not trust all the parameters, like, for example, like the stars too close to the limit. So surprisingly, if you look at one of our stars, there is a good agreement. Of course, you can say, yeah, I'm sure it's the best example. Yes, it's the best example, because examples for which the VR bars are bigger, so not so good agreement. But if you want to find a bad example, just read my paper. And so if we want to compare the temperature fine for the group C between the temperature fine from the group group B, sorry, we can say that it's more or less the same temperature, but the error bars are getting bigger and bigger because we are more and more affected by the circumstellar dust. And well, you can say that more or less the fits are okay, let's say. But we start to see some spectral issues, for example here, but I'm going to talk about it later. So let's see now what we can get for the group D. First things I want to point out is that so the group D is for the stars with a G-K higher than 1.6, and all the stars with the 1.53 micron feature, just based on visual inspection. And it's interesting to note that all the stars in our sample are mirror-type stars, but not all the mirror-type stars are the 1.53 micron feature. Like, for example, if you look at that one, this one, they don't have the 1.53 micron feature. And so this red star starts to be more and more affected by pulsation. So now before seeing some fits, we have to ask ourselves a question. Okay, we want to reproduce a star with the 1.53 micron feature, but do we have this feature in the models? Yes, we got it. So it's if we look at some molecular indices, almost the same plot as I showed before. The group are a little bit different. So A, B, C, as I presented, and D, all the stars with the 1.53 micron feature. You can see that some of the models have this feature, this absorption feature at 1.53 micron. But if we want to see the smooth appearance, we don't have it, but it's expected because we are working with dust-free model. So I would say that's normal. So let's move now to the comparison. It's where it's become interesting. So the visible temperature of 3,300, you can say, yeah, why not? And if you look at the near-infrared, a temperature of 2,700 Kelvin, so we say, yeah, it sounds reasonable. We've got the 1.53 micron feature, not exactly the same shape, but yeah, that's okay. But if you look now at the round of models that are considered to be good, it's like almost all the models are good. So you get a big range of values. So it's between I think it's between 2,400 and almost 4,000 Kelvin. And in that case, it's interesting to see that okay, we've got this low temperature, 2,700 Kelvin, but we got also high surface gravity, log G equal 2. So do we trust this one? Say, yeah, maybe not. But I've got another example for the group D, and now more interestingly, we've got the temperature of 4,000 Kelvin for one of the radius carbon stars that we've got, so like no way. But now we've got the log G that we want. So let's say for the parameters from the group D, we don't believe them, and we say that they have to be used with great cautions, and that's why we need the dynamical models. Because here, clearly, we are trying to fit dust around, but we are not fitting the feature. Or if we are fitting the features, we have the surface gravity. So two spectral issues that I mentioned before. So the part on the left is C2 lines at 1.77 micron. And so you got in black our observation, in white what is called the best model. And I would say this line seems to be reproduced quite well, I would say. Okay, but we've got a difference here. We've got a line at 1.75 micron, which is not in the models. And furthermore, if we look at the feature at 1.53 micron, so we were happy because we said, yeah, fine, we got the feature, we can reproduce the stars. But you can see that the shape of the features between our observations and the models are not the same. So clearly, we need to, well, the modelers need to revise their line list. So I think, as a conclusion, so we did a comparison between the our carbon star spectra we model. We did a low resolution at 2000. And I can say that there is a good overlap between the temperatures that we found in the visible and in the infrared. And of course, as we move towards redust objects, the overlaps get bigger and bigger. And you can also say that the grid of parameters is not large enough, but of course, we can add more models afterwards. Yeah, so it becomes more and more difficult to deal with the redust carbon stars because you are more affected by pulsation, dust, and everything, and all these things which are not present in the hydrostatic models. So we already knew this. But it was good to see what we can do with hydrostatic models. And so, of course, the next step will be to move towards the dynamical models to see if we can reproduce all this redust stuff. And it would be also interesting to do a study of the molecular stratification. So the idea, for example, would be to see if this feature at 1.53 micron, so HCN plus C2H2, where is it located? So we think that it's located, it's intermixed with the dust, so that's why it appears larger in the carbon stars with this feature than other features, because all the other features, I would say, are smooth and lower. And last but not least, it will be interesting to do this study that I just showed with the hydrostatic models at a higher resolution, and just to see which features are well reproduced on them. So we already know that, for example, for C2 and HCN is not the case, but we have to study other features. And I think I'm just going to conclude, to finish by saying thanks to the organizer. And if you want to see more about XSL, just go to listen to the talk done by Anke and see the poster made by Gustavo and Natalia. Sorry, Natalia, I forget your name. Thank you.
Questions?
How bright is stars?
Sorry?
How bright is stars? How faint is stars? How faint is stars?
What's that called? Well, I don't know the word.
Magnitudes.
Look at the white.
I mean, if it's a shorter grain sample, I can tell that it's J magnitudes from 3 to 10.
Yeah, so we got a new XSL expert. Just ask me, go here.
No, I'm just looking at it.
Because I followed them up with my instrument.
Whether you can get optical counterparts.
Oh, the optical extremely faint.
Well, you get all these optical. For the warmers, it's easier. Yes, sir.
You mentioned dynamical models. Do they already exist, or what's the state? How far along are we?
Yeah, so you got already dynamical models, but the issue is that they are very low resolution, like I think 200 if I'm not mistaken. So we've been fighting over the last years to get some models, and well, we are still waiting. That's why the comparison is not done, but so we think that now one step could be to just do a very low resolution comparison with the dynamical model, at least to see what is working. And that's why we are doing this work, just to dynamical models that we need dynamical model, because what's the point to get extruder? Okay, the resolution is like 10,000, and doing the resolution at already 2,000, so it's already lower than the resolution. But what's the point to, if you want to do a comparison with dynamical models at a very, very low resolution? I mean, it's good, but it would be even better if we can do the high resolution models. But I think it's just a matter of computation time. Yeah.
So you showed a star in NGC 121. I think that was group B or so.
Yeah, what would it be?
So was this a cluster member star? Or is it just in the direction of this? Maybe I'm wrong. No, another slide, I guess. No,
Ah,
this
no,
before.
120.
And you just see, yeah, there's one. So is that a cluster star?
Yeah, I think so.
Because the metallicity you showed was minus 0.5 and the cluster metallicity is minus 1.4. So I was wondering if you have, yeah, this one.
Yes.
So I was wondering if there's some systematic or it's real, have some hints on that. Because it's like 1 off of the average metallicity of the cluster.
Well, I would say that the grids that we got only 2 metallicities, so it's either 0 or minus 1.5. So I would say I would trust more minus 0.5 than 0 for these stars.
Yeah.
But yeah, we got also a denoisy between temperature and metallicity. So
That's what I was wondering, because maybe we can use this to calibrate the metallicity and to have a better constraint. There is high resolution for this cluster, like RGB stars, so maybe this could be a proxy.
yeah, that's good. Good to know. Thanks.
More questions? No, let's thank our speaker.
Thank you, sorry about getting used to next. So yeah, thank you very much. It's very good to be here today. It's a pleasure to be in Brazil for the first time. So enjoying the warm weather, that's for sure. So I'm going to talk about the AMBER Spectral Library. This is a project I worked on when I was a postdoc in Nice. So just, I've talked about AMBER at the last two Spectral Libraries workshops, so it's nice to advance it from my last two talks. So where we are with AMBER, so to remind you, AMBER is a project that was between ESO and the Observatoire della Côte d'Azur to determine the stellar parameters for the archive spectra of the Pharos, UVES, HARPS, and spectrographs. So it was a lot of data that turned up at Nice with a variety of wavelengths and resolutions, and not just constrained to the stars. We got everything that came, all the calibration files, any kind of object. So a big part of this project, and that was my role, was to put a pipeline around the parameterization algorithm, Matisse, put a pipeline around that to sort of filter out as much as possible of the non-stellar objects and use Matisse to determine the parameters. So it took a lot of work and a lot of time, but we eventually got there. There are two main outcomes from this project in terms of spectral libraries. The first is the AMBA synthetic spectra grid, which is what we used within Matisse to do the determination of the parameters. So that was one resource as well. And then the other was the production of the temperature, gravity, metallicity, and alpha element abundances for as many of the stars as possible within these archive data sets. So we got there with Pharos, Harps, and UVES. We finished those and just published the UVES paper last year. But Flames Giraffe is a whole can of worms with many setups, a lot of data. It'd be very useful data, but kind of having a break and got to figure out how to best approach that data set. So that's sort of on hold at the moment. But we've got a lot of results with Pharos, Harps, and so to describe the synthetic spectra grid, because this is also being used not just in AMBA but in many other projects. This was a grid calculated by Patrick Delaverny at Nice, who's who I was working for. It's based on the Mars stellar atmosphere models, the FGK and parameter range, and so these are just some illustrations of the grid points in metallicity, log-G, and temperature and alpha space. Just to give you an idea of what coverage there is, certainly in the HR diagram. So it's not, trying not to cover particularly non-physical areas, but reasonably well spaced, particularly where we know we see a lot of objects to give us that resolution. Then in metallicity, again, pretty well coverage over solar and less well spaced going down to more metal 4 stars. And again, just showing the metallicity space. And then the alphas, we followed alpha metallicity. So each metallicity point has about 5 alpha points. So it covers a nice range in parameter space and is generated at very high resolution, greater than 150,000, that can be convolved and sliced up to however everybody wants to use it. And the best way to get hold of it is just to email Patrick to interact with him about it. So I went through how it's being used actually, just to see what different people are doing with it. And certainly it's being used a lot as the basis for automated stellar parameter analyses, global full spectrum fitting type analyses is particularly useful for. So Matisse is the algorithm that we used for AMBA. And as well as AMBA, it's also being used in the, by Alejandro Vicer Blanco in the Gaia RBS analysis for parameters and so forth. And in Gaia RESO, a couple of nodes, I was one of them doing UVES analysis using Matisse. So that's one that's a connection to Nice. I was also looking up the references, and there's Galfray, which Marika Valentini. So she uses that in a chi-squared analysis. So that was nice to see other parameterization codes using it as well. SICK by Andy Casey, I don't know why he wanted to call it that, but anyway, his program has the AMBA as an option to use the synthetic grid, and was used by Louise Howes in the analysis of some A and omega stars for the Middle 4 program. So that was really interesting to see as well. Also Galar, picking up, I guess, from Andy's work and Louise and the Australians, their recent paper on their analysis pipeline, they use it for the radial velocity and the stellar parameterization determinations. So it's being used in a variety of places. And then some more maybe science analyses, well, not science analyses. So one use that's come up, I'm involved now at Cambridge in the Weave and Foremost surveys, and we're in an operational rehearsal for Weave at the moment, just testing out our data flow, and have used, wrong way around, sorry, have used the OMBA grid for simulated spectra for passing through the data flow. We're about to try using it. So that's one quite interesting use of a synthetic spectral grid as well, and one that I think would come up more and more, or as these big surveys are going online, I'm going to need these sort of synthetic spectra to do this testing of. So I think this is a really to be thinking about if your libraries can be used like that. And then this was an interesting paper using the grid for estimating the continuum of certain fluxes around calcium 2 features for rotation activity correlations with KMM dwarfs. I don't know anything about it, but I thought it was just a really nice use a different use for the grid. So that's the synthetic spectral grid, and it's out there available for use. But what I was working on particularly was determining the parameters for OMBA, and this is where we got to with our products and the 3 papers we produced. So in terms of stellar parameters, we got per spectra from ESO, and we generated parameters per sector and then could figure out how many stars. And this is sort of the breakdown. So for Pharos, it was about 6,500 spectra that we got parameters for. It was about 30% of the total sample. So we had to, well, a lot was discarded simply because they weren't in the parameter range or the quality of the spectra or so forth. But that came to about 3,000 stars, and 11,000, we determined radial velocities for about 12,000 stars, so that's useful as well. For HARPS, 90,000 spectra, we got the parameters for 71% of the sample, not unexpected given HARPS is planet hunting, so it's optimized really for the MARCS parameter space. So about 10,000 stars, which is a really nice sample. And then UVS, just finished last year, about 12,000 spectra, again 24% of the sample. But yes, we're not doing parameters for supernova and all that sort of thing, not quite relevant for a spectral grid, but about 3,700 stars. This just shows the wavelengths that we used per analysis. So Pharos, we had the full spectral range, but so this is 3,000 to 10,000, but we took chunks of that. The dark blocks are the high telluric contamination regions, and the grey blocks are not so high, but just to be aware of. Certainly when we came to do the red 860 setup, we didn't have a lot to work with due to the telluric contamination. So Pharos HARPS was, again, good spectral coverage. The UVS, we had 6 standard setups that we focused on from all that we got. So 3 blue and 3 red settings. So they were very challenging. We had to deal with each one of those separately. So there was a lot of interesting work here, understanding the characteristics of the different spectral ranges. And this is what we got out in terms of HR diagrams. I really like looking at these. I think they're pretty, but ones I might be a bit of a mess. It's a metallicity color bar. So I like this one. I think if you close one eye, it's red, and you close the other eye, it's blue. But you get the idea of the giant branch moving from the metal rich to the metal poor. So, so for each HR diagram, you can see sort of the focus of the set that we got out. Again, so Pharos being more solar metallicity, so this range of metallicities, with a few interesting groups of maybe metal poor stars. HARPS, again, the focus is on these hunting for stars with planets, so looking at more solar type stars. So that's definitely comes out in the HR diagram, and again some interesting features here. And then for UVS, well, UVS is used to chase a lot of metal core type objects. So again, there's quite a large metal core sample. So we've got these parameters now. It was really great to get to this point and go, right, now we're trying to do bits of science along the way, but it was nice to round these off and actually start playing with this data. So that's the type of projects we've tried to look at. I'm going to go through a few of these, not all of them, but just to give you a feel for the types of investigations we've done. So certainly it's they're each large data sets in all different directions. And lots of different types of objects. So comparing, for one thing, for Pheros, we were trying to look at the PPMXL subsample, try to give a bit of order to this chaotic sample. But then you can pull out, say, the globular clusters, open cluster samples. But as well as trying to look for big population samples, just looking at small stellar evolution samples, trying to trace how, for a particular type of stellar evolutionary stage, what interesting things we might find there. And that was something I particularly wanted to look at. Looking at middle core stars, I've got a master's student digging into that at the moment. And then so Paolo used some of my AMBER parameters on a confirmation of in her paper just to confirm, help to confirm some of the stellar twin work that she's working on. So that was a really nice use as well. And then we do actually have some papers out, so I'll talk about these as well, which is extending the AMBER sample to now include abundances. And then finally, Gaia DR1's come along. So I think everybody's sort of taken their favorite data set and cross-matched it, had a look at stuff. So I'll just show you that as well. So with AMBER and the archive spectra, it's a compilation of a whole lot of different proposals. So you never want to talk about selection functions with AMBER because it's such this disparate group of a whole lot of different purposes, I suppose. But because it's such a large sample, it would be nice to try to bring some sort of definition to it in terms of how it fits as a population sample in the Milky Way. And this is what I did sort of early on when we had the Pheros results and didn't have Gaia yet, was to try to bootstrap the AMBER results onto something that had a defined sample. So using PPMXL, so compilation of proper motion catalogs, and then also Hipparcos. So looking within the Pheros sample to see what we had of those groups. And so AMBER Pheros, at the time I was looking at about 2,000 stars. Cross-matching that with PPXL, we got about 1,000 stars out. So that was, so this is a dwarf sample, sorry, this is a giant sample. And then Hipparcos is about 700 stars. So looking at the metallicity distribution of these three samples, just trying to say, well, is the AMBER sample reflecting the distribution that we get from these well-defined samples? And for the dwarfs, so Hipparcos in black, PPXL in blue, and then Pheros in cyan. And the agreement is very good in terms of the peak of these metallicity distributions. And then the spread on the Gaussians as well. So for the dwarfs, certainly we could argue, well, the dwarfs within AMBER Pheros are looking pretty good for being able to be used for a population type study, and the metallicity is reflecting the typical population as well. So, and certainly seem to be solar neighborhood, which makes sense. Pheros is on a 4-meter telescope, so that's, and looking at dwarfs, you're kind of not going to extend much past the solar neighborhood. The giants are a different story, certainly. We're probing different depths between brighter, can look a bit further. So trying to do this bootstrapping didn't really work so well, again, because the samples, I think, will just be quite different. So the Hipparcos sample, so we can see sort of this movement of the peak of the distributions here. So I wouldn't rely on the giants so much, or at all really, if you're trying to do that sort of analysis, but the dwarfs are looking quite useful. So that was a nice exploration. Just a look at the globular clusters, and particularly in UV's Red 580, because there's quite a nice sample in there. We had quite a selection of differing numbers of stars. People have done a program, or there were a couple of different programs, we could bring them together. So here we've got Ruprecht, is that? Omega Sen. My eyesight is really terrible, so I can't remember. can't read them, so sorry, I should have put them in bigger. I think what's nice about these metallicity distributions, I should at least say that, of 5 of the globular clusters, and omega-7 pops out really nicely, the expected very multimodal, I guess, metallicity distribution of omega-7, so it's nice to have that confirmation of the OMBA analysis. And then I think this is NDC 6752, which has something interesting going on here. But otherwise, the metallicity distributions are looking fairly symmetric, I think. We also get alphas out for the OMBA analysis. So just looking at the alpha versus metallicity graph for the different, the selection of globular clusters. Again, we've got omega-7 here, which is quite a large range. So I like to put it up because it just shows, you know, something that's a unique object. But otherwise, really high alphas at low metallicity, and then this more less high alphas and sort of medium middle poor. So it's a nice set to explore with. This is sort of as far as I've gotten with this data set. I'd like to add more elements and abundances into it and explore that further. But certainly it was a nice confirmation of the OMBA results as well. And one thing I really wanted to dig into was just to look at, you could try to look in at big samples, but just to look at a small sample and try to dig in to find some interesting objects. For my PhD, I was looking at chemical abundances in giant stars and globular clusters, looking at like 50 stars, which seemed a lot at the time. But here I really wanted to get back to that because I was looking for the chemical signatures of AGB and so forth. So this was me trying to just also try to set up an abundance analysis of some of the spectra. So this was looking at the HARPS spectrum, pulling out the sort of the giant stars. In this HR diagram, the grey are all per spectra analyses results. So we reduced that to a per star results. So I pulled out about 200 stars with low log G, and then went about trying to measure a variety of elements, trying to reflect different pollution or nuclear synthesis sites. So some supernova, giant branch AGB, RGB, thermally pulsing AGB, and so forth. So, so this was, yeah, an interesting exploration, and I got sort of so far with it. I really like these graphs. So this is your abundance against atomic number. This is for the lowest log G set from less than 1.8 in log G, and we have been from 2.25 to 1.8. 2.75 to 2.25, and then greater than 2.75. So just was like looking at this chemical signature and effect of these different bins to see if there was anything interesting particularly. And pulled out this particular one as showing sort of two signatures going on, one that sort of goes up and down like this. And thought, that's kind of interesting, I'll explore that a bit further. And particularly was looking to see what of these elements sort of go with each other. Can we expect to see the products from similar stages, so from AGB, RGB, the different stages there, would they go with each other or not? And this sort of sets, which isn't defined by distance or where they are in the galaxy, they're very much, here they are in the HR diagram, what's interesting about them. So this plot just showing sodium against a global metallicity that we get from OMBA, and then I recalculated the individual ion abundances as well. So this set seemed to have a split in metallicity. So I just arbitrarily placed that and then explored what they did in the other elements. So silicon to sodium, calcium to zirconium, and barium. And the main thing that popped out was in the more metal-rich bin, though it's only about minus 0.25, was this trend with zirconium. With sodium. And so I thought that was quite interesting, not altogether sure what it means. So you've got sodium as a product from AGB, RGB, zirconium from thermally pulsing AGBs as well. So sort of perhaps indicative of a common pollution site. It's not really a metallicity relation because we've constrained it to quite a small metallicity range. So I thought that was quite an interesting feature. That's about as far as I've got with that project. Need to explore that more, dig out some more elements. So this HARPS is a full wavelength range. I just looked at a particular section that I had already set up for abundance analysis, but certainly can pull out things like europium, look for technetium, for the variety of things I can further look at. And there are these works by Hassan and also out of the paper by Feltzing, looking at how these trends between elements as you go between metal rich and metal poor. So there's an interesting work to continue when I have it in my non-existent spare time, but these sort of talks motivate me to get back into them. So the NICE team have been also working on different aspects of science exploitation of AMBA. So there are a couple of papers that came out last year looking in different aspects of this. Guillaume Guillaume, who's a PhD at NICE, derived lithium abundances for dwarfs in the ferrous HARPS and UVETS data sets, ignoring the lithium abundances for this sample. So we got about 3,000 dwarfs. And this is the key plot, I guess, the lithium abundance derived from non-LTE against metallicity, showing a couple of comparison papers, but also showing this split plateau and the Big Bang nucleosynthesis from audio value. I've got negatives here. I just got trigger happy with my negatives, but you know. What they found was at metal poor, the distribution was akin to the split plateau, but then increasing by about 1 dex to solar metallicity. So that confirms chemical models and other studies, as you can see here with the comparison. So it's a nice confirmation of the lithium abundance is determined for AMBA, and then they found this decrease in lithium for supersolar stars. They then broke the sample down into looking at the thick and thin disk, because to look at the chemical evolution histories of these two populations. So we have the thick disk, or the thin disk in blue and the thick disk in red. What they found was that there was differing chemical enrichment in lithium for these two subsamples, that the thick disk has more low chemical enrichment, as we can see from this slope, starting pretty close to the split plateau. And then the thin disk having this high enrichment going to solar. They also pulled out a metal-rich, alpha-rich sample. So this is the breakdown here of the histograms of the abundance in lithium and normalized distribution. So we have, again, the thick disk, the thin disk in blue, and then this metal-rich population showing two peaks in the lithium abundances. So showing perhaps more another interesting element to the enrichment history for that, that population. So that's been an interesting study in lithium. And then Sharunas Michaelatis, he was a postdoc at NICE for a while, deriving a lot of element abundances for the big sets of the AMBA spectra. So this in particular is looking at the iron element abundances in the solar neighborhood. A mainly dwarf sample, but about 4,000, I think, dwarf stars, and a few giants in there as well. But what, and as Christina was saying in her talk, we need these big samples for making the comparisons, of these chemical evolution models. So Sharina separates in this plot. We've got magnesium, manganese, nickel, copper, and zinc, and separating them by thin disk, this metal-rich, high alphas, thick disk, and then metal poor, two metal poor groupings. So really nicely shows these different populations in these element abundances, and so very useful for chemical abundance comparisons. And so we did that comparing these distributions to chemical models. I just put the caption up because there was a lot of there was a lot of models that he made comparisons to. And so this is quite a very nice set of a high number of stars across a nice metallicity range. Here he constrains it to -0.8 to 0.4, showing how some elements are matching quite well to the models, where others seem to be quite off. And then finally, using the sample to explore different discriminators. Don't necessarily have to compare everything to iron every time, and certainly this is showing, so this is against the various elements against metallicity, but here it's against magnesium, and showing, I mean, the ranges in the axes are the same, but here the distinction in the populations is much greater. So, and particularly for the manganese on magnesium set. So using the sample to explore other diagnostics that can be used for chemical evolution comparisons. So then finally, the last bit of I've sort of been playing with and doing explorations with myself, but also the team at NICE, looking particularly at it more, looking at the cross-match with Gaia DR1 and Typo 2, doing the velocity type work as well. But this is just a sort of a look at the different samples. So we've got UVs and HARPs, and this is the HR diagram with the metallicity color map. And this is the sample that is cross-matched with T-gas. So it was about, I think, 1,000 stars each. So really quite a nice sample. Again, UVs, we've got color map and metallicity, so we can see the metal rich and metal poor samples. For HARPs, again, it's more solar, but we've got these slightly more metal poor subsets, but again, a very nice consistent sample of solar metallicity. This is just putting up the Gaia G magnitudes against the T-gas distance, so just do 1 over the parallax. So certainly more solar neighborhood in both samples, UVs with a few more points stretching further away, but the sample is pretty much concentrated within the 1 kiloparsec. So I wanted to just look at that to come, to take the distances and just look to see where these are in terms of the actual diagrams in the alpha versus metallicity plots. So this, I've constrained the distance to, so now we've got a distance color map, constrained it between 0 and 1 kiloparsec. It certainly shows our giants are the ones that are more distant, so that makes sense. And brighter ones, so we're going to probe for the distances. And where they pop up in the alpha metallicity diagrams for each of these. So UVs have certainly got a larger thick disk sample, but again, mainly dominated by dwarfs and not really dominated by very distant objects, but there are a few. We can sort of see them dotted in here. For HARPs, there's not much in terms of giants, but we've got a dwarf-dominated sample. Then in the alpha range, we've got this weird interesting sub-alpha sort of population here, which we need to explore a bit more. The sample is really just this little blip here, but again, we're not sampling so far in distance for HARPs. So there's again an interesting sample cross-matching with feed gas, fairly sizable sample as well to do some investigations with, and combined with NICE, going to be exploring this a bit more to bring in all of the kinematic type information. So that was really all I had to show, sort of a showcase of different projects that we are actually now using for AMBER in terms of science exploration, which is really great to be at that point. So also the synthetic spectral grid is being used for a variety of purposes, and I think that and the different projects also for the parameters are making this a very useful data set. One problem with the parameters is that we have to make them available only through ESO. Under the agreement, we can't put them up on CDS, which is kind of frustrating. and they are a bit hidden in ESO for trying to extract them. So we're kind of working on a way to make them more generally available, because I think there's some interesting science that can be done. And certainly that's a lesson learned. And if you want your data to be out there being used, make sure you are in control of how you want to make it available publicly. But certainly the connections that the team has with various groups means we've been able to get it used in different ways to do so. So then on Thursday, so I'm chairing the roundtable discussion on filling the gaps in this conceptual library stacks. And this was, I was wanting to ask the question of how can we maybe develop more spectral libraries in this era of very large spectroscopic surveys that are going on. So I tried to show that OMBA, we've used it in a variety of ways and is being used in large-scale surveys, but so many of the libraries that we're going to present over this week, maybe you might try to think more about how they could be used in this big survey era. And whether you want them to or not, that's another question. But also we've got people here, so Christina's talk and Rodolfo's here as well, who are working in these big surveys and could have ideas about how there are gaps that these stellar libraries might fill. So that was just something to get you thinking about now, and I'll be wandering around and asking people to have some thoughts for that discussion on Thursday. So otherwise, thank you.
Thanks for that talk. Just one comment regarding the control of public access to the library. Wouldn't it be possible, for instance, to share not the library itself, but the scripts and the configuration that were used to produce the library? So anyone could just reproduce the library. Even if ISO does not allow you to share the library itself,
yeah,
you cannot control the configuration, right?
Right. So that's a good idea. So you mean like, well, the parameters were generated with Matisse algorithm, which Nice don't really let out of Nice. So,
but Albert wants it to be released, right?
Sorry?
Albert Perry wants Matisse to be released.
Yeah, so the Matisse algorithm, the way it's been used, it's usually in collaboration, and it's done, processing's done in Nice. So, yes, so good idea. But, yeah. Sorry.
You go back to the plot of the global clusters, please.
Oh, sure. Oh, right. All right, I can do it that way. Easy too. It's really good.
Yes. So 2 points caught my attention there, because you're using UV spectra.
Yes. So this
but even though the error bars are a bit higher than usually UV's analysis, I mean, it's 0.1, 0.2 that, as you can see from the metallicity.
The metallicity is more rich than you'd expect to see. Is that what you're saying?
No, it was just the error bars.
Oh,
Error bars
error
are larger
bars.
than I would expect from UV's data.
Yes.
So what's taken into account in the error bars?
So the error bars, we do an error analysis looking at primarily how the repetition of the parameterization goes with signal to noise. So because we get multiple spectra of the same object, so we take out a calibration sample, actually Pastel, I meant to mention that, we use the Pastel library and the Gaia benchmarks as a calibration sample to see how the repeatability of the parameters goes. We're actually overly cautious in parameter range. I guess so, yeah, these are more the spread of the results as well. So, yeah, I need to think about, I can't remember how I calculated these errors. So,
And maybe there's some systematic errors included, it's not only the average,
Yeah,
maybe the models. And
yes.
stuff like that.
Yeah, that's a good point.
The other point is that, I mean, in particular for the metal reach, was double checking the metallistes. They're usually roughly okay, but the metal reach are more metal poor than expected. I mean, in particular for the NGC 6528, version 7, they have metallicity above -0.2 or so.
Oh, right, okay.
And they are very metal poor here. So I don't know. I know that for metal reach it's tricky to fit, but I don't know if you have some comments on that. Or...
Yeah, that's a nice comment, because I hadn't looked, gone in more detail than this to like do the comparison to accepted values and to see where we are with things. Yes, so I do need to do that check. So, but yeah, it's a good point. Yeah, it's a good observation. Thank you.
I have a question regarding, again, the metalist determination. How sensitive is it to the, let's say, relative flux calibration errors and problems with the data reduction in US in particular? Because if you go quite far to the past, the data that you can get from the ESO archive, they were used using very old pipelines, and they were not very good.
Well, I guess I didn't say that. So we had spectra from about 2009, 2010 to, yeah. And they were all re-reduced with the new, with whatever the current version was that they were going to make available as advanced data products. So I think there was a re-reduction of everything, or at least that.
So you didn't include UMS POP because it was like 2002, 2003.
No. And I might have looked at UMS POP as a calibration sample, but I just pull out the key stars, so I didn't take that as a reduced spectra to put through.
It's great talk. I find very interesting the result of the Umbra project with the lithium for the metal reach. Before we really jump on that, why is this? It's very important to really be sure about the metal reach end, because things there move depending on whom we talk and what we try. But that is potentially a very interesting thing. Very nice to see that there is such an overlap between TKS and amazing.
Yeah.
Even for the dwarfs. There it's very important now if we have the overlap that we are doing the same with the overlap between APG and TGAS and another sample that is an overlap between RAVE and TGAS.
Yeah.
But that there you have more information on the dwarfs, so you're very local. So it's very interesting to take those plots and compute the orbits that you can for those stars and clean this plot and look the plot always in guiding radii local. See, take out the stars that due to eccentricity are passing around, and then look again to that plot.
Right.
That would be very nice to do it.
Yes. So working with, is it Michael Hager who's in these now? Yeah, so he's
coming to us.
Oh, right.
He
Okay.
just arrived.
Okay, cool. So I think he's actually looking at doing the orbit analysis for all the TGS Umbra crossmatch. So yeah, so that's exactly been really going to, yeah.
Claire, well done. You produced, reproduced a great deal of science, and it was a lot to digest all at once. Two things came to my mind, one of which worries me, one which might worry you. One that worries me is to do with lithium again. I was wondering I couldn't remember what resolution were those abundances based on?
So HARPS is a very high resolution, it's more than 40, or it's 40. 100,000, yeah.
Was that the basis of the other plots you showed with the resolution of the lithium abundances?
Yes.
I mention this simply because there is, within about half an angstrom, there is another blended feature of metals of the iron group elements, right close to that lithium line.
Okay.
And I wondered to what extent there could be some confusion when we've got higher metallicity stars.
That's a fair point. I guess so when we did the parameter analysis, we convolved it down to lower resolutions, about 40. So when I was working with it, we convolved it down to those resolutions.
40,000, you can see the
But for the actual abundance analysis, again, I think we've just use the resolution as it was, so at this highest level. So I don't recall him particularly checking that, if there'd be this blending with the feature that you're saying, but yeah, something I can certainly go and ask him.
Yeah, okay. And the other feature thing is a bit more fundamental. All of this, when all is said and done, the whole thing depends on modelling stars, which is usually done in a fairly swashbuckling way. And when you look at the sun itself, it's the only star we can actually see what it's like at all. It's got an atmosphere, which is where the stars come from, which is turbulent, and streaming in different ways, and it's stratified, and it's got all sorts of nasty things going on. Does that worry you?
Well, yes. I think with doing this and also being involved in the bioresource survey and looking at how many different methods and the variety of what we think we know something, but we have different methods to do the analysis, and they're not as in good agreement as we might like. And trying to understand those differences, and Paolo's done a lot of work in trying to understand how we're getting differences between different different methods for analysis. And yeah, so I think it does worry me. I think, but it also worries sufficiently other people that they're trying to explore it and try to understand a bit more as well.
Thank you.
Further applause. It's too late. So let's encourage people again.
We are going for lunch now. We come back at 2:30. And if you want to leave your stuff here, you can leave it. The door will be locked. Okay, so.